The follow excuse me. The following data refer to a 4-cylinder internal combustion engine operating on a 4-stroke cycle at 4,400 revolutions per minute. Volume compression ratio 7.6 to 1. Cylinder diameter 78 millimeter. Stroke 105 millimeter. Brake power 38 kilowatts. Indicated power 47.5 kilowatts. Air consumption 21 kilogram per kilogram of fuel. Fuel consumption 13.6 kilogram per hour. Energy released during combustion of kilogram of fuel 41,800 kilojoule. So they want us to determine the mechanical efficiency and the mean effective pressure. The volumetric efficiency referred to 1 atmosphere, which is equal to 101.225 kilopascal. The brake thermal efficiency. The brake thermal efficiency ratio relative to the air standard cycle. So it is further suggested to use R, which is 0.287 kilojoule per kilogram Kelvin. Okay, let's first see how we can determine the mechanical efficiency. We know that the mechanical efficiency. Okay, before I do that, I will first show the power distribution in the engine. So we have the input. The input is basically the energy from the fuel. So the input energy is due to the calorific value of the fuel. So we have the input power, which is converted into indicated power. So we have the indicated power here, or we can just symbolize it by IP. So what is the indicated power? The indicated power is basically the power that is caused by the combustions. So during the combustion, we know that the pressure increases and the piston is pushed downward in order to produce work. So that work is called indicated. So the rate of that work is called indicated power. So it's basically the power of the diagram. So the PV diagram. So from the input power to the indicated power, there is so we basically need to one basically need to convert the input into a pressure, which is the indicated power. So during the transformation, there is always a loss occurring. So the input power cannot be equal or greater or less than the indicated power, because there is some loss occurring in the system. So now the energy, the indicated power can also be converted into mechanical power. So the mechanical power is what is also called brake power. Why is it called brake power? Is because they use the braking system to to determine the value of the power on the shaft. So it can be a pulley or something else. So now, what is converted into the power which is converted into a brake power is that one, not the input. So here we have the first loss. So these are the losses due to friction. So they are, we can also call them thermal losses. So these losses are so here we have the first kind of loss, which is due to which is caused by the waste of heat from the system. So it's called thermal losses. And the second type of loss is, so from the input to the indicated power we have, in order for this transformation to take place, in order for the fuel to be transformed into indicated power, we need they need to be a thermal losses. But we cannot transform energy and without losses. So from the indicated power to the brake power, we also have some losses. So that's kind of losses due to friction. So we have the friction losses. So the brake power is basically the power collected on the shaft of the engine. So now, how to determine the brake power? To determine the brake power, we need the torque and the rotational speed. So the power, the brake power is given by 2 pi n over 60 multiplied by the torque. So that is the torque collected at the shaft of the engine. So now here we have the first question. They want us to determine the mechanical efficiency. So we cannot determine the mechanical efficiency if we don't have the brake power and the indicated power. We first need to determine the brake power and the indicated power, because the mechanical efficiency is the ratio of the brake power and the indicated power. So let's first determine the brake power, which is given by this relation. So we are given the rotational speed. So in this case, as you can see, the rotational speed is expressed in revolution per minute. If it was expressed in revolution per second, we wouldn't divide this expression by 6. In other words, we wouldn't include that 60. So we put 60 when the value is given in revolution per minute, not in revolution per second. So if I work this, I just need to substitute by the value. Do I have the torque? Okay, let me see. Okay, here in fact we don't even need to determine the brake power because it is given. So we just need to determine the indicated power in order to determine the efficiency. Okay, let me see. So we also have the indicated power. So we have the brake power and the indicated power. So you can easily get the mechanical efficiency. So you don't need to use all this formula. So what is the formula of the mechanical efficiency? Given by the brake power divided by the indicated power and then multiplied by 100. So if we replace, we have the brake power, which is 38 kilowatts. So we also have the indicated power, which is 47.5. So now if I compute this, so I have 38 divided by 47.5 multiplied by 100. So I have 80%. So question A is completed. So now in question B they want us to determine the volumetric efficiency. Refer to 1 atmosphere is equal to 101.325 kilopascal. So the volumetric efficiency is symbolized by this notation. So in B they want us to determine the volumetric efficiency. No, the mean effective pressure. So the only expression that has the mean effective pressure is the indicated power. We know that indicated power is given by PL. So you use the weight plane so we can easily remember the formula. So the P means so that P represents the mean effective pressure. So L is the stroke and A is the area. It's basically the area of the piston, which can be determined from its diameter. So N represents the rotational speed and E represents the number of cylinders. So now here we just need to, so we can make PM subject to formula. So we can say PM is equal to, so send all this to the other side, so it becomes indicated power divided by L, A and E. So we have already determined the indicated power. No, we didn't determine it, but it was given already. So we have the indicated power, which is 47.5. So we have the stroke and the area. If we read properly, we can see that the stroke is 105. So I need to convert that into meter. So we have 0.105 multiplied by, so we have the area that can be calculated from the diameter. Okay, in order to save more space, I can just use the second line. So that is given by, so we have the indicated power, which is 47.5. So we have L, which is 0.015 multiplied by the area. So the area can be determined from the diameter. So that is the diameter of the cylinder, which is given by, so the area will be 0.78 square multiplied by pi over 4. So we use the relation of the pi d square over 4 relation to determine the area. So all this represents the area. And then we have the rotational speed. So we have the rotational speed. In this case, we are going to express the rotational speed as the number of firing stroke for one revolution. So we have the rotational speed, which is how much? But in this case, we need to make sure that the rotational speed is expressed in revolution per second. So this value should be converted into revolution per second. So we need to divide by 60. So now that N represents the number of firing stroke per revolution. For a 4-stroke engine, we need to divide that N. So the value of N is the rotational speed divided by 2. So we need to divide the rotational speed by 2 again. So we divide by 6 because we need to convert the RPM, it means the revolution per minute, into revolution per second, because this formula only work with revolution per second, not revolution per minute. And then we need to divide by 2 because it is a 4-stroke engine. So as it is specified here, we have a 4-stroke engine. For a 4-stroke engine, we have one firing stroke. So we have one firing stroke per revolution. So that's why we have divided by 2. I mean, we have one firing stroke for 2 revolutions. In order to produce one firing stroke, we need, so the shaft needs to rotate 2 times. So that's why we need to divide the value by 2. So now we also need to multiply by E. What does E represent? E represents the number of cylinders. So never confuse this 4-stroke and 4-cylinder. They are not the same. 4-stroke means the firing stroke occurs in 2 revolutions of the shaft. 4-cylinder is just the number of cylinders. So we are going to multiply this by 4. So now if we work this out, we get 645.5 kilopascal. So that's the mean effective pressure. So now we need to do question C. So in C they want us to determine the volumetric efficiency. So what is the volumetric efficiency? So it's simply the ratio between the induced volume divided by the swept volume. So the induced volume should be expressed in cubic meter per minute, as well as the swept volume. So we have NV, which is given by induced volume divided by the swept volume. So if we have the engine, okay, let's assume that this is a spark ignition engine. So we have that is the cycle. So the swept volume is the volume from that point to there. So it's basically the volume described by the piston displacement. So that is called swept volume. So it's also symbolized by Vs. So now the induced volume is just the amount of air which is being supplied to the engine. So if we work this out, the induced volume is always less than the swept volume. So it means the air being supplied to the engines, the amount of air which is being supplied to the engine is always less than the induced volume. The volume of the cylinder. Otherwise, if they were the same, we would get a volumetric efficiency of 100%. But that is not in reality, it is not the case. So now, how to determine the volumetric efficiency? So we can find the volumetric efficiency using the relation of, we can find the induced volume using the relation of ideal gas. So we know that PV is equal to mRT. So from this relation we can determine the volumetric, we can determine the volume. So we first need to determine the induced volume and then find the volumetric efficiency later on. So V is equal to mRT divided by P. So here the volume will be expressed in cubic meter if I consider the mass. If the mass is not 1 kilogram, so we can also determine the rate of volume induced. So that represents the rate of the volume rate. So in order to get the volume rate, we need to make sure that we have the mass rate on this side. So this mass rate is for air. So this relation is applied only with air, not other gas, because we have the value of gamma, which is 0.287. It can also be applied to other gas, but in this case we are only dealing with air. So that's why they are referring to the air standard efficiency, because this is the air standard cycle. So now how to determine the mass rate of air? If I have the air fuel ratio, the air fuel ratio is given by the mass rate of air divided by the mass rate of fuel. So we can use the mass rate or the mass, it depends on what is given. So that gives the air fuel ratio. So I can determine the mass rate of air if I have the value of the air fuel ratio and the mass rate of fuel. So if I replace, because here I need to use the mass of air. So that represents the mass of air, and this is also the induced volume. But here you can see that the mass of air is not given, because I need to determine the mass rate. So the one that is given is called the air fuel ratio, because they say air consumption 21 kilogram of fuel. So that simply means that for 1 kilogram of fuel, we have 21 kilogram of air. So we have the induced volume, which is given by this relation. So, and the air fuel ratio, which is given by this relation here. So then we can determine the mass of air while cross multiplying these two. While just multiplying these two. So if we cross multiply, we are going to say the mass of air is equal to the mass rate of fuel multiplied by the air fuel ratio. So that means air fuel ratio. AF stands for air fuel ratio. So I'm gonna have the mass of air, which is given which is then equal to so I have the mass rate of fuel, it is given already. So I need to convert that into kilogram per minute. So that means I'm gonna need to divide this by 60, because the fuel consumption is expressed in kilogram per hour. So I'm gonna need to divide it by 6 in order to get my mass rate in kilogram per minute. So I have 13.6 divided by 60. So that is the mass rate of fuel in kilogram per minute. Then if I multiply by the air fuel ratio, I get the mass rate of air. So the air fuel ratio is that one. So the unit is kilogram per kilogram. So that represents the unit. So that 21 kilogram per kilogram simply means that the mixture is made of 21 kilogram of air and 1 kilogram of 1 kilogram of fuel. So we need to multiply it by 21, which is the air fuel ratio. So then the air fuel ratio is so we have 13.6 multiplied by 21 divided by 60. So that represents the mass rate of air, kilogram per minute. So now, if I have the mass rate of air, I can determine the induced volume. All I need to do here is I'm gonna need to use this relation. So the induced volume is given by the mass of air, which is 40. So here the induced volume will be expressed in cubic meter per minute, because the mass rate is expressed in kilogram per minute. So the unit of induced volume depends on the unit of the mass rate. So I just need to replace what I have into this relation. So I have 4.76 multiplied by R, which is 0.287 multiplied by, so I have the temperature. So that is basically the ambient temperature. So where can I see the temperature here? Okay, here the temperature is 0 degrees Celsius. It is specified in this way, so I'm gonna need to rectify a little bit this phrase, or there is a continuity. In the textbook, when you read, it is written that, so it is written 1.325 kilopascal, and the temperature is 0 degrees Celsius. So I need to convert that 0 degrees Celsius into Kelvin. So it's gonna be 273 Kelvin. So I'm gonna use that 273 here. Okay, let me work this on the new page. So in the previous slide, we stop here. So we need to find the induced volume. So we need the induced volume in order to determine the volumetric efficiency. So I couldn't write the formula, the expression on this space because it is too small. So here, if I use, so it starts with this relation here, PV is equal to mRT, or I can use the volume rate. So that's gonna be my induced volume, which gonna be equal to mRT over P. So I've already determined the mass rate of air, which is 4.76. So I did that from the previous slide. So that was done in the previous slide. So I have 4.76. So I have the value of R, which is 0.87. 0.287. And then I have the temperature, because I've explained in the previous slide that the volumetric efficiency were said to be calculated at this pressure and this temperature here. So the pressure is 1 atmosphere, which is equal to 101.225 kilopascal, and the temperature is 0 degrees Celsius. So since we need to convert, since we are working with Kelvin, then we need to convert that 0 degrees Celsius into Kelvin. So that gives 273 Kelvin divided by the pressure. So the pressure is 101.325 kilopascal. So now when I work this out, I'm gonna determine the induced volume. So to determine the induced volume, if I calculate here, the induced volume is 4.76. So the induced volume is 3.681 cubic meter per minute. So next I'm gonna need to determine the swept volume. The swept volume it's gonna be expressed into cubic meter per minute as well. So we first need to determine the volume of the cylinder, because the swept volume is basically the volume of the cylinder. So the volume of the cylinder is given by the we have the area multiplied by the stroke. So we have the area multiplied by the stroke. So that gives, so the area is pi d square over 4 multiplied by the stroke. So that gives pi multiplied by, so we have the diameter, which is 0.078 square divided by 4 multiplied by the stroke, So the stroke length is 0.105. So that gives, so if I work this out, I get so I get 0.000501728 cubic meter. So that is the swept volume, but I need to express that into cubic meter per minute. There is a possibility because I have the rotational speed. So now here there is something we also need to so the volume that I've just calculated is for one cylinder. So that is a volume of one cylinder. So to find the volume of multiple cylinder, I'm gonna divide. So to find the total volume, I'm gonna need to multiply this by 4. So I'm gonna say the swept volume times 4, which gonna be equal to, I need to take this number multiply by 4. So I get 0.0020069 cubic meter. So now I need to convert the volume in cubic meter into the volume rate. So there is a link between the volume and the volume rate, which is the revolution per minute. So I can say that the volume rate is equal to the volume, so I need to multiply by the rotational speed, which is given. So and then I need to divide it by 2. Why I need to do so? Because we have a 4-stroke cycle. In the 4-stroke cycle, we have one induction stroke per 2 revolution. So one induction stroke equal in 2 revolution. So that's why I need to divide by 2. So that makes sense because we have we only have one suction stroke for 2 revolution. So if I now replace this, I'm gonna have so I multiply by the rotational speed, which is 44 and 00 divided by 2. So that is the swept volume. So that is the total swept volume. I call it total because I've multiplied by the number of cylinder. So that is the total swept volume. So this is expressed in cubic meter, but this is expressed in cubic meter per minute. So if I work this out, I'm gonna get so I get 4.415 cubic meter per minute. So now we have the swept volume and the so we have the induction volume or induced volume as well as the swept volume. So we need these two quantity in order to determine the volumetric efficiency of the engine. So we have the new slide here. So now I'm gonna use the formula. So I know that the volumetric efficiency is equal to induced volume divided by the induced swept volume, which is symbolized by Vs. So these are the value that was determined from the previous slide. So we have the induced volume, and then we have the swept volume. So it's basically expressed in percentage, so we need to multiply by 100. So now if I compute this, I'm gonna end up with so the value is 89.34%. So now we need to do question. So we need to solve question D. In question D, they want us to determine the brake thermal efficiency. So what is brake thermal efficiency? So the brake thermal efficiency is the ratio so we have the which is symbolized by NB, which is the ratio of the brake power divided by the energy of fuel. So in other words, it's the overall efficiency. Or it's also called total efficiency. So brake thermal efficiency is the same as total efficiency. So we have already the brake power, which is, I can see it here. So we have 38 divided by, so what is the energy of fuel? So we just need to look at this value. So this is not a power, but I need to make sure that I'm working with power, because I have the power, which means the rate of energy. So I have power on top, so I need to make sure that I also have the power at the bottom. So power, it simply means the rate of energy. So that needs to be expressed in kilojoule per second, because my first power is expressed in kilowatts, because kilowatt is the same as kilojoule per second. So I also need to make sure that this value here is expressed in kilojoule per second, and this is the mass of fuel. So to get this value to convert this value into kilojoule per second, I'm going to need to multiply it by the mass rate of fuel, because we know that power is equal to mass rate multiplied by the energy. So I have the calorific value of fuel, which is 41,800 kilojoule. So I need to multiply this with the mass rate of fuel. So I have the mass rate of fuel, which is expressed in kilogram per hour. So I need to make sure that I get that value in kilogram per second. So from hour to seconds, I need to multiply by 160. So I have, okay, first copy the mass rate, and then I'm gonna need to divide by 360. Why I need to divide? Because that hour is at the bottom, it is not on top. So now I just need to compute this relation here. So I have 41,800 38 divided by 41,800 multiplied by 13.6 divided by 360, 3,600. So I get 24 points. So I need to multiply this by 100 in order to express it in percentage. So I get 24.06%. So that this is what is called break thermal efficiencies. In other words, it's a total efficiency. So I'll just write a note here. So now we need to do the last question. In the last question, they want us to determine the thermal efficiency ratio relative to the air standard cycle. So they recommend us to use R, which is 0.287 kilojoule per kilogram. So I need to create a new slide for this. Okay, so the break thermal efficiency ratio is given by this relation. So that is the break thermal efficiency ratio, so which is symbolized by NB. I mean that this one is symbolized by NE, which is given by the following expression. It's just the ratio between NB. NB means the break thermal efficiency divided by the air standard thermal efficiency. So that is called air standard thermal efficiency, and this one is called break thermal efficiency. So if I divide the break thermal efficiency with the air standard efficiency, I'm gonna get the break thermal efficiency ratio. So it is expressed in percentage, so I'm gonna need to make sure that the value is in percentage. So I've already determined this value here. I've determined that from the previous slide, so I just need to determine this one too. So how to determine the air standard efficiency? So we use a well-known relation. So the air standard efficiency is given by 1 minus 1 over R to the power of gamma minus 1. So that's all I need to do. So I have 1 minus, so I have the value of R. Okay, let's R represents the volumetric ratio, which is 7.6. So I need to use 7.6 there, and then have gamma, which is 1.4 minus 1. So now if I work this out using the calculator, so I will have 1 minus 0.443, so which is equal to 55.57%. So if I got that into percentage, so now, so I just determine this this value here. So now I'm gonna need to determine what is asked in question D. So they want me to determine the break thermal efficiency. So the break thermal efficiency is given by the break thermal efficiency ratio, which is given by this relation here. So I need to get the break power from the previous, I need to get the break power thermal efficiency from the previous relation. So we have this, which is 24.06. So I have 24.06 divided by the air standard thermal efficiency, which is 55.57. So I need to multiply by 100. So if I do that, I'm gonna get the value here. So this is a new slide. So I have the break thermal efficiency ratio, which is if I work out the expression that I had in the previous slide, so the value will be 43.3%. That's it.